Records. Let's not forget this. Okay, guys, we have already finished all these parts, right? Now we are going to talk about the last part of this chapter. As I told you, I just skipped 4.8 Green's functions on purpose. There is nothing big, so that we are not going to use this anywhere in our subsequent chapters, like in chapter 5, 6, 7, 8. But if you're interested, you can see this and all the just some new notations, some new different approach. Okay, it's all about Green's functions. And 4.9, solving systems of linear differential equations by elimination. Let's talk about this. Non-linear differential equations. There's also, I will skip this. You can study yourself, self-studying, just 3 or 4 examples, some different ideas. Okay. And I'll see, maybe we may talk a little bit about nonlinear differential equations. There's not much also here. And also, especially we'll focus on nonlinear differential equations in chapter 6, when we talk about power series solutions of differential equations. Okay, so solving systems of differential equations by elimination. Because the method of systematic elimination uncouples a system into distinct linear ODEs in each dependent variable, this section gives you an opportunity to practice what you learn in sections 4.3, 4.4, 4.5, and 4.6. Anyway, here, so far, we have been dealing with a single differential equation, right? As you see from high school or from pre-calculus, sometimes we have to solve a system of equations, a system of linear equations, or system of, in general, equations, right? Maybe sometimes one equation is linear, another one is non-linear. I mean, algebra. How do you solve this? If you remember, when you actually studied simultaneous equations or linear equations, we learned 3 different methods, right? One is substitution method, another one is elimination method, third one is graphical method. I always say to the students that this elimination method, that is most commonly used method. Even they use that idea in linear algebra and also here solving differential equations. Okay, the idea is very similar. I mean, in terms of eliminating one variable or more variables from the system. Okay, bring this a system of equations into a single equation. Then we have to solve it, and after that, using this, we can get the second variable, the third one, and fourth one, blah blah blah. Okay, and what is different here? The concepts, because we are talking about differential equations, so the vocabulary, the concepts are different because our system involves the derivatives of the functions. Okay, and also you are familiar with this, right? How to solve a single differential equation, how to write a general solution, and if it is initial value problem, and also we know how to write the solution. Okay. All right. Here, what do we mean by systematic elimination? The elimination of an unknown in a system of linear differential equations is expedited by rewriting each equation in the system in differential operator notation. Okay. So here, the main idea is we can also use this prime notation or Leibniz notation or the other notations. We have a few different notations for derivative, right? So now I'm going to introduce, maybe before actually, I already told about this differential operator. All right, I'm going to introduce this operator. Let's say this D, okay, actually it's a kind of notation. Let's say it is D over D, for example, let's say T. All right, I'm just denoting this thing because it's a kind of operation, right? It is performing some kind of operation over a function. Because if you differentiate a function, right, it produces different function, right? By just applying this operator. So this thing, let me just denote this by capital D. Okay. For example, let's say if you're given 2 different functions, a function of t, x, and y is a function of t, for example, how do I write this thing? dx dt, right? Using this differential operator, I can write it as actually this means that we are differentiating given function with respect to t, right? So what is this d dt? D dt is capital D. So I can just write it as capital dx. How about this thing, for example, I said dy dt, right? So that thing is equal to d dt, and I am differentiating here the function y, and y with respect to t. So what is d dt? We denoted this by this capital D. So that is, I can just simply write it dy. As you see here, if you just compare these two notations, dy dt and just dy, which one is simpler? This one is simpler, right? And in some, actually, in especially differential equations, and a lot of times you have to write the derivative of the function using this notation. But since they are using a lot, in some cases, of course, in some situations, expressing this one or writing this thing in terms of, this form, it is more convenient in terms of saving time, in terms of using things or letters, right? So this is actually, we are calling differential operator. Okay, again, why operator? Because it's performing some kind of operation, right, on a function. And when you just perform or apply this d on a function, it produces a new function. Okay, now if you see this example, for example, here we have nth order linear differential equation, right? And also, how can I write this using this differential operator? So this one is d to the power n. That means that here, this operation, right? What is it doing here? It is differentiating a given function n times. This is how you should understand. This means that, for example, y here, and this means that it is differentiating a function n minus 1 times, right? And also because of the linearity property of the differential operator, I can take this out, right? As you see here in this example, for example, this thing, okay, d dt is equal to this, right? For example, if I have to write, how about this one? dx dt plus dy dt, right? What does it mean? Differentiates x with respect to t, differentiate y with respect to t, right? And also, actually, I can write this one as d dt, right? Differentiates first x plus y added, then differentiate, they're the same thing, right? So that means that here, if I have dx plus dy, I can write it as dx plus y. Okay, it's like our algebra. As you see here, when we just write d, even we do not see any, what is the prime notation, right? For example, here, if I convert this into, write this system of equations, differential equations, using differential operator, right? As you see here, we have second order. So this x is differentiated with respect to t twice. So here we have d squared x here, and plus 2 times x prime. So that here we have dx, right? And minus x, there's nothing. Here we have x. So here we have x here. If I just take this out, instead we have d squared plus 2d minus 1 x. And the similar way, here we have d squared y minus 3 times y. If you just take this y out, here we have d squared minus 3y. And the second one, second row, the second equation, x prime minus 4x. So here we have dx, right? So it is dx minus 4x. X is a common factor, take this out. And also here we have dy minus 2 times y. Y is a common factor, take this out. Here we have d minus 2. And actually it's capital D minus 2 times y. On the right hand side, we have just e to the power negative t in the first one, sine of t. Okay. And this is how we are actually writing the given differential equations using differential operator. Actually, it was used in annihilation method in 4.6, I think, something. But we skipped this because there was nothing new, only that did this using this differential operator. Okay. So our topic here is to solve system of linear differential equations. And also we know that when we are solving a system of equations, right? It is a system of linear equations or system of equation, whatever it is, we need to find a common interval, right? That is the interval of solution. Actually, that must all equations in the system should make sense, right? Because in this interval, when you pick any input value and substitute into the function, it makes sense. It makes sense means we are able to evaluate the value of the function. And that's why we call this here a solution of a system of differential equation is a set of sufficiently differentiable functions, right? Because it must be differential, otherwise it doesn't make sense. Assume that here we have a function, and I'm claiming that this is the solution of the function, but we cannot differentiate this in a given interval. Doesn't make sense, because here the equation involves the derivatives of the function. So that's why we are saying that sufficiently differentiable means if we have first order, we should be able to differentiate this once. If it is a second order, we should be able to differentiate this twice, right? Depending on the order of the function, I mean, derivative of the function in the system. So here, if you're talking about a system, maybe in the system, how many dependent variables we have? We may have 2, we may have 3, we may have 4, at least 2. Since we're talking about system, that means that we have 2 equations in the system, right? We may have n, right? If the first dependent variable is x, independent variable is t, let's say we just, after solving this, we got this solution, and for y, it is this solution, for z, this solution, and so on. So that satisfies each equation in the system on some common interval, right? Common interval means actually that is the common interval for all these functions. If you just pick any input value from this interval, we should be able to evaluate these functions at this point, right? Otherwise, okay, for example, one interval from 0 to 5, okay, for each value on this interval, we can evaluate the value of the function here, also for y, but here, it's not defined, for example. It doesn't make sense. That's why it should be common interval, means that we have input variables. Actually, when we just substitute into this, right, we should be able to evaluate these functions, okay? All right, gentlemen, now let's focus on the method of solution. Assume that we are given the system of differential equations, okay? We have to solve this. In different way we can solve this, but here we're going to solve this using the differential operator. Using the previous notation, what we have here, this dx dy, dx dt, not dy. I can just write it as dx, right? And this one, dy dt, right? I can write it as just dy, right? Now, if I substitute here, what we have here? If I substitute here, we have dx equals 3y, and here we have dy is equal to 2x. Okay, these are not independent variables. If they are not independent variables, we better keep them on the left hand side, right? If we have independent variable, what is independent variable here? It is t. If you have something in terms of t, you can keep this on the right hand side, right? We need to write this in standard form. So if you just take this to the left hand side, then this equation becomes here dx minus 3y is equal to 0. The second one is dy minus 2x is equal to 0, right? System of differential equations. And also they are linear because we do not have the product of 2 independent variables here, right? So how do you solve this now? Now see here, we have a system, right? 2 different equations. So we are going to use here elimination methods. So I will eliminate either x or y, it doesn't matter. Usually in alphabetical order, if you just go in this way, I have to eliminate this y. How can I eliminate this y? Let me rewrite this in the right order. So here we have dx minus 3y is equal to 0. The second one is, if I just multiply both sides by -1, here we have 2x minus dy is equal to 0, right? Now, here, let me just multiply both sides by d. But now you should understand, when I multiply by d, that means that I'm just applying the differential operator. That means that differentiating, right? Both sides. So if I just multiply by d, what we have here, in the first equation, we'll have d times d. d squared x minus 3dy is equal to d times 0 is equal to 0. Now if I multiply the second one by 3, right? So here we have 6x minus 3dy is equal to 0. These equation systems are exactly the same, not same, but they are equivalent. Equivalent means their solutions are exactly the same. Okay, so from here, if I subtract the second equation from the first one, what happens here? Since they're the same, right, I'm going to eliminate this part. So we will have here d squared x minus 6x is equal to 0. Okay, now from here, I can write it as d squared minus 6, and here we have x is equal to 0. If we just write prime notation, what we have here? Here we have x double prime minus 6x is equal to 0, right? How do you solve this? Let's see here, when we just use differential operator, it is just easy to convert this or to get auxiliary equation. What is the auxiliary equation of this homogeneous equation? That's just simply, instead of d, I need to write m squared minus 6 is equal to 0. Or m is equal to plus minus square root of 6, right? So from here, let me just continue in this way. So I can write the solution of this one, right? Now what is x of t, right? Because we are looking for x, that's equal to c sub 1 times, right? Here we have what is the independent variable, it is t. So here we have e to the power minus square root of 6t plus c sub 2 e to the power square root of 6t, right? Okay, that's the idea. Now in similar way, I can find y, right? How can you find y? To find y, for example, give me a minute because I need more space. Let me just add one more slide. Okay. All right, so that is our x. Okay. Now let me find y here in the second part because I need the equation. All right. So our equation is, now we need to find y, right? So that is dx minus 3y is equal to 0. And the second one is 2x minus dy is equal to 0. So now I'm going to eliminate x so that I can get y. Here I should multiply by 2. So here we have 2dx minus 6y is equal to 0. And multiply by d, 2dx minus d squared y is equal to 0. Right? And subtract the second equation from the first one. We have d squared y minus 6y is equal to 0. Or d squared minus 6, it is y is equal to 0. That is exactly the same, right? Similar, just only y is different because here also m equals plus minus square root of 6. But now if you just write the solution for this differential equation, what we have here, c sub 3, right? E to the power minus square root of 6t plus c sub 4 times e to the power square root of 6t. Okay. How about the x? Here x is x of t equals c sub 1 e to the power minus square root of 6t plus c sub 2 e to the power square root of 6t. Right. These constants are different as you see here. But here we have two systems, two equations, but here we have four constants, right? And if we, actually this system does not or is not satisfied for every value of C1, C2, C3, C4, right? Somehow they are dependent on each other. How can I identify this? Because here we have two equations, and also we have this constant must be 2. Okay, to do this one, now I will substitute this into this equation. Okay, now I need to determine this C3, C sub 3, C sub 4. All right, if you substitute here, D, okay, number 3, let's see, let me change. All right, if I substitute here, dx minus 3y, right? Now we know we know what this means, right? This dx means just the differential operator applied to this. That means that we need to differentiate this once. If you differentiate this thing once, what we have here? Here we have negative square root of 6 c sub 1 times e to the power minus square root of 6 t, right? And also for this, plus square root of 6 c sub 2 e to the power square root of 6 t. That is our dx. Minus 3, what is y? Y equals this. So here we have c sub 3 e to the power minus square root of 6 t plus c sub 4 e to the power square root of 6 t. Right? Now if I just simplify this, as see here on the right hand side we have 0. And I can all write 0 here. That's equal to, if you simplify this, that is the common factor, right? Take this out. What I have here, minus square root of 6 c sub 1, right? And here we have minus 3 c sub 3 e to the power minus square root of 6 t plus, and this thing is square root of 6 c sub 2 minus 3 times c sub 4, right? Minus 3. So here we have e to the power square root of 6t. Now on the right hand side, this should be identically equal to 0. Okay, but here sometimes they just use equal sign. But here it's not our usual equation. This is not an equation. This is an identity. What does it mean? It means that if this I is the solution of interval, let's say I is the solution of interval, if you just pick any t from the solution of that interval, that's a common interval, right? If you substitute here and evaluate this, it must produce 0. I mean, this expression should be exactly equal to 0 when you simplify and evaluate this. For every value of t from this interval of solution, that's identically equal to 0. But see here, this function e to the power minus square root of 6t and e to the power square root of 6 times t, these functions are linearly independent, right? How do you know that? We know that this function, if you multiply by any constant, is never equal to this function. Only we have two functions. The simple definition is this, right? So the only way when their linear combination is equal to 0, if these things, their coefficients, this must be equal to 0 and this must be equal to 0. Okay. Now from here I can find c sub 3. C sub 3 is equal to, take to the right hand side, divide by 3. So here we have minus square root of 6 over 3 c sub 1. In a similar way, what is c sub 4? C sub 4 is equal to square root of 6 over 3 c sub 2. Okay. So now if I substitute here, then we can write the solution of this system. Let's write green, dots, dots, dots. What is x? X of t is equal to c sub 1 e to the power minus square root of 6 t plus c sub 2 e to the power square root of 6 t. And y of t equals c sub 3. What is c sub 3? Equals this. Minus square root of 6 over 3 c sub 1 e to the power minus square root of 6 t. And c sub 4 plus square root of 6 over 4 c sub 2 e to the power square root of 6 t. That is the solution of this system. Okay. And again, we know what we mean by this. If you just substitute here, and if you substitute the value of y into here, right, evaluate this, it will be identical equal to 0. And this thing substitute into this equation, and this y substitute into this equation, differentiate and evaluate this is exactly equal to 0. Okay? For every value of C1 and C2, for every value of C1 and C2. But here, it was not enough. If you substitute here, it's not equal to 0 for every value of C1 and C2. Because if you just substitute these two things here, you will get some kind of equation like this. Okay, they are not exactly equal to 0. Okay, so we need to add, or we need to continue one more step, and also we need to identify this. So there's a special relationship between these coefficients, right? C1 and C3, and C2 and C4. And they are related to each other by these two equations. Okay, Rotvisan, are you there?
Yes.
Did you get the idea?
A little bit.
Yeah, this is very simple equation. As you see, is a bit long, but not so complicated. But we have to go through all the steps, otherwise we cannot solve it. That is differential equation. As I told you, sometimes one simple equation, we need to, how to say, full maybe 3-4 pages. But the system is very simple, but that's a solution. In case what we saw, if you have better solutions, shorter solution, let me know. We can publish paper together, okay? So far, the known method is this. All right, now you'll see that if I just, the question is a little bit bigger, it involves more terms. You will say that it's much longer than this. But the idea here, what is important for you, you are civil engineering students, here how things are working together. As you see here, we just add one more equation. Now we are talking about the system. If you add one more system, right, one more equation, 3 equations, more parameters, it is more complicated. More complicated means, I mean, the description will be quite different. And also in real life, when you're building a house, it is something like this, right? All these components are related to each other by some kind of relation, like the beam of the house and the roof and the ceiling, right? And the height of the room and the size of the wall. These are all parameters. So we should try to do this in the best way so that, I don't know, actually it'll be more and more successful. You can serve your people much better. Okay. Anyway, this is math. This is how we solve system of linear differential equations by elimination. If you have no question, now you got the idea. Let's just solve a bit more different question and go a bit faster, because I just explained very slowly so that you get the idea. Okay. So let's say another example. We have 10 minutes, unfortunately. Other examples, maybe I will record it and share with you on YouTube. Okay. Example 1, solution by elimination. Now you got the idea. What should I do here? I'm going to eliminate y here, for example. So the first step, let me continue from here. First step, here we have d plus 2y, here we have y, right? So first I multiply the first equation by 2. Then here we have 2dx plus 2d plus 2y is equal to 0. The second one multiplied by d plus 2. So here we have d plus 2, d plus 3, right? Sorry, it is minus. So it is minus, right? And here we have x minus 2 multiplied by d plus 2. So here we have d plus 2, y is equal to 0. Now if I add the first equation to the second equation, already the signs are opposite, right? They cancel out each other. What we have here, if you just add them together, here we have d plus 2, d minus 3x, right? Plus 2dx is equal to 0, right? And x is a common factor. If we just remove the brackets and simplify, I get something in d. Here we have x is equal to 0. So here we have d times d squared. We don't have d squared here. We just write d squared here. Negative 3d plus positive 2d, or just 2d. The sum is minus d plus 2d. That is plus d, right? And 2 times -3, that is -6, and times here we have x equals 0. And you know how to write the auxiliary equation? That's just simply m squared plus m minus 6 is equal to 0. And just quadratic the equation. If you solve this by factorization, m plus 3 and the m minus 2, that's equal to 0. Okay. So m sub 1 equals -3, m sub 2 equals 2. Now, how to write the solution here? Then x of t is equal to c sub 1 times e to the power -3t plus c sub 2 times e to the power 2t. Right? So we actually determine here x function. In a similar way, let me just do here. Now I'm going to eliminate this x. Here we have d, here we have d minus 3. So the first one I should multiply by d minus 3. So here we have d minus 3x plus d plus 2 d minus 3y is equal to 0. Multiply both sides by d minus 3. The second one by d plus 2. So here we have d plus 2 d minus 3. Sorry. The second one, we should not multiply by d, right? So here we have d minus 3x, and this one is minus 2dy is equal to 0. Okay. So d minus 3x, d minus 3x. If you subtract the second equation from the first one, what we have here, and also simplify this, here we have d squared and minus 3d plus 2d, that is minus d and the minus 6, right? And we are subtracting plus 2d, and here we have y is equal to 0, right? And if you simplify this, what do we have here? D squared plus d minus 6 y is equal to 0. Here we have d squared plus d plus c. It's exactly the same, right? It's not always, but of course here in this question is the same. So here y is only different, and here we can write this y of t is equal to c sub 3 e to the power minus 3t plus c sub 4 e to the power 2t. That is the solution of y. I don't need this line. It's, all right. Let me just change my marker color and continue. We got x of t, we got y of t, and the last thing is now we need to determine this c sub 3, c sub 4. Because for every value of c1, c2, c3, c4, this is not satisfied, right? Okay. Now, if we substitute here in the first equation, again, it doesn't matter. It's just substitute this in the first equation, the second equation, it doesn't matter. If we just substitute the first equation, so here we have dx plus d plus 2y is equal to, what is dx? Dx means I need to differentiate this with respect to t once. So here we have minus 3 c sub 1 e to the power minus 3t. Plus, this one is 2 c sub 2 e to the power 2t. Right? Plus, now here we have, what we have here, dy. What is dy? dy is minus 3 c sub 3 e to the power minus 3t plus 2 times c sub 4 e to the power 2 sub t. Okay. Now here we have plus 2y. So here we have plus 2 times y. What is y? Y equals this. So here we have c sub 3 e to the power minus 3t plus c sub 4 e to the power 2t. Okay. Now if you just simplify this, on the right hand side we have 0. This e to the power minus 3t is a common factor, right? So let me just write here. First, here we have minus 3c sub 1 right? And here we have minus 3c sub 3, right? And here we have plus 2c sub 3 e to the power minus 3t plus how about e to the power 2t? Here its coefficient is 2c sub 2. And the second one is here it is plus 2c sub 4, right? And the plus here we have what we have here. Here we have c sub 3, c sub 4, 2 c sub 4. E to the power 2t, it is identically equal to 0. Okay. Now from here, minus 3 sub 3, c sub 3, right? It is minus c sub 3. What is c sub 3? Is equal to minus 3c sub 1. From here, it is 6, right? What is c sub 4? It is minus 1 over 3 c sub 2 minus. All right. Now, just see x of t is equal to this. Instead of c sub 3, if you just write this thing and substitute here, and instead of c sub 4, write this thing and write here, right? And that gives us the solution of the given differential equation. So I can just add it here, y of t and is equal to c sub 3. It is minus 3c sub 1 e to the power minus 3t, right? And here we have minus 1 over 3. Is it 1 over 3? This one is 4, c sub 4, 1 over 2. This one is 2, right? It is 4 minus, okay, minus 1 over 2 e to the power c sub 2 times e to the power 2t, okay? That is, these things are the solution of the given system of differential equations. Okay, guys, that much is enough for today. Other examples, maybe we'll continue tomorrow, okay, or I may record the video and share with you. We have less than 1 minute left. Thank you very much. If you have more questions, you can ask through Telegram, okay? See you tomorrow. Enjoy your lunch. Bye-bye. That's enough for today. Thank you.
Goodbye, sir.
Bye, sir.
Bye-bye. Bye-bye. Thank you.